Today we're going to learn about the osmosis and how it's really just passive diffusion of water across a membrane, which we've already talked about in a previous lesson, but we're going to take it to the next level. Just as solute molecules will passively diffuse their concentration gradients, water molecules will also move from areas of high concentration to areas of low concentration to equalize the concentration of water inside and outside of the cell, which you probably already know. The diffusion of water across a membrane is simply a special type of passive transport that we call osmosis. And just as solute molecules may diffuse across a plasma membrane, molecules of water also move across the membrane, equalizing the water concentration inside and outside the cell. Now, although some water can pass through the lipid bilayer, the hydrophobic region severely limits this. Most of the rapid movement of water in and out of cells occurs through water channels, which are called aquaporins. It's kind of like aquapores, like pores of your skin, but it's aquaporins, P-O-R-I-N-S, aquaporins. These are transmembrane proteins with hydrophilic channels through which water molecules can pass in a single file type of manner. Osmosis can have some dramatic effects on cells. As we see in the image here, many molecules just can't move across the cell membrane. But while the molecule can't move out of the cell and down its concentration gradient, water can move into the cell down its concentration gradient. And as water diffuses into the cell, obviously, will get larger. When a cell is in a fluid environment, referred to as a solution, the amount of dissolved substances, or what we call solutes, in that solution may be either equal to, less than, or greater than the concentration of dissolved substances in the cell. This relationship between the concentrations of solutes inside the cell and solutes outside the cell is referred to as tonicity. T-O-N-I-C-I-T-Y. You can see this also in an image being displayed currently. So first, the concentration of solutes outside the cell is equal to the concentration inside the cell. The outside solution is considered isotonic. Water still moves between the solution and the cell, but because it moves at the same rate in both directions, there's no real net change in the amount of water inside versus outside the cell. Now, second, if the concentration of the solutes outside the cell is lower than the concentration inside the cell, the outside solution is hypotonic. In this situation, if the cell membrane is not permeable to the solutes, more water will move into the cell than out of it, and the cell will swell. Lastly, if the concentration of solutes outside the cell is higher than the concentration inside the cell, the outside solution is called hypertonic. If in this situation, if the cell membrane is not permeable to the solutes, more water will move out of the cell than into the cell, and the cell will shrivel up. You actually see osmosis in action in your own kitchen. Take a look at this image displayed here. If you take if you take a stalk of celery, I guess that's what it's called, right? Yeah, if you take a stalk of celery and leave it on the counter for a couple of hours, what's going to happen? Well, as the water evaporates from the cells of the celery stalk, it's going to shrink and become flimsy and limp. You can make it firm and crisp again by placing it in a solution of distilled water. Well, why distilled water? Well, it's because it contains very few dissolved molecules, so it's a hypotonic solution. Cells in the celery stalk, on the other hand, contain many dissolved molecules, such as salt. Because these dissolved molecules can't easily pass across the plasma membrane of the celery stalk cells, the water molecules move down their concentration gradient and into the celery cells. Would the celery regain its crispness if you placed it in a concentrated salt water? Well, no, because there are more dissolved solute molecules and fewer water molecules in the hypertonic salt solution than inside the celery cells. what little water remains in the celery cells would actually move by osmosis out of the celery, causing it to shrivel even more. A more practical use of osmosis is seen with the laxative, which is called milk of magnesia. This product contains magnesium salts, which are poorly absorbed from the digestive tract. As a consequence, after a dose of the laxative, water moves by osmosis from the surrounding cells into the intestines. The water softens the feces in the intestines and increases the fecal volume, thereby relieving constipation. It's important to note that the direction of osmosis is determined only by a difference in the total concentration of all of the molecules dissolved in the water. It doesn't matter what the solutes are, only how many molecules of solutes there are. To determine which way the water molecules will move, you need to determine the total amount of dissolved stuff on either side of the membrane. The water will move toward the side with the greater concentration of solute. For this reason, even small increases in the salinity of lakes can have disastrous consequences for the organisms living there, from fish to bacteria. Conversely, putting animal cells, such as red blood cells, in distilled water causes them to explode, because water will diffuse into the cell, which contains more solutes, and the cell will swell and eventually burst. This doesn't generally happen to plant cells because, as we'll see later in this unit, the plant cell plasma membrane is surrounded by that rigid cell wall that limits the amount of cell possible when water moves in by osmosis.